Hi there, and thanks for attending this RSS workshop. Over the next few minutes, it'll be my pleasure to talk to you about robots thinking fast and slow. It's not so much a retrospective, really, but more of a particular way of looking at the intersection of machine learning and robotics, really rooted in my own experience in trying to get robots to act and interact in the real world over the past decade or so. And the realization, really, that there now exists a real opportunity in revisiting concepts from psychology and cognitive science to build safe, robust, and efficient robots. And that's really, really exciting. Right, now, so you'll all be already aware of what machine learning is, so I don't really want to dwell on that, but it is useful to establish a common set of nouns that I can use to get my point across. So machine learning is essentially an associative process mapping an input to a particular output. So traditionally these mappings are classifications like depicted here, so it might be, cat is like cat or dog is of class dog. And one way of looking at the learned model itself is through the lens of knowledge distillation, right? So during training there may well be some oracle whose knowledge gets distilled into the learner. So in this case it might be human provided labels. Okay, so we've been able to do this for decades, right? So what's changed? You may have guessed, deep learning's come along, right? And again, I don't really want to dwell on how it works, but only what it really affords us in the context of the story, which is really twofold. So first of all, we can now accurately learn some pretty complex mappings. And secondly, we can take these mappings and execute them very quickly indeed. And that's really important for what's next. Of course, there's also a third thing, which is very close to my heart, which is the learning of structured latent representations, but time in the spotlight is short. This fits into this narrative, but we can't really go here now, so apologies for that, but that's for a virtual beer at some point. Okay, so let me give you a couple of examples. There are really thousands of them, but let me focus on a couple of reasonably well-known ones, just to draw your attention to the kind of thing that I'm talking about. So we've got gameplay here, where you map from a particular game state to the next move and the value of that particular game state, for example. So think of things like AlphaGo, think of things like StarCraft, right? Autonomous driving has been a pretty high-profile application of robotics and machine learning in the past few years. So think of applications like taking a street scene and using a machine learner, or a learned model in this case, to map to a segmentation of where a human might drive in that particular context. Think of intuitive physics, which is really a big one right now. So think of taking as an input the perceived state of a particular system and using a machine learning model to predict forward how that state evolves in time, for example. Like here we are saying, is this block tower stable or not? And of course, robot control. So think of things like visual motor control, or in this particular case, the OpenAI work on taking and training a learner to control a shadow hand to maneuver a particular block into a specified target position, right? So all of these are examples of mappings that are now possible. Now, each one of these also comes, of course, with its own oracle to learn from, right? So on the left here, we've got all the learners. On the right, we've got the corresponding oracles. In case of the classification task, it might be human-generated labels. In the case of gameplay, it might be Monte Carlo tree search rollouts. In the case of autonomous driving, it might be the hundreds of person years of systems engineering that goes into this in order to equip the car, put the sensors on, calibrate, have other systems that predict ego motion and so on. In the case of intuitive physics, it might be writing down the laws of physics and embedding them into, for example, a simulator. And in the case of control, in this case it was things like learning by trial and error through reinforcement learning, and parallelizing the process in such a way that effective learning is possible within a tractable number of hours. So all of that hugely exciting and very well done. But that distinction is really quite important for where we're headed with this narrative, because I can take it and put different labels on it, in the sense that on the left we have systems that are very fast. They're very fast to execute, whereas on the right the oracles are really quite slow, right? And slow here means, in some sense, resource intensive, right? So it means it takes time, it takes expense, it takes experience, prior knowledge, and so on to really gather that knowledge before it can be distilled into one of those learners, and that's important. Now, all of that's interesting because it has been suggested that a similar separation between systems really exists in cognitive science, right, and behavioral psychology. So dual process theory, as popularized by Danny Kahneman's book Thinking Fast and Slow, essentially suggests that one thing that makes us humans operate robustly and effectively is the interplay between two types of processes. So there's a fast, intuitive process, system 1, and a slow, deliberate, reasoning one, system 2. And here I have brazenly copied some of Denny's adjectives to describe these two systems, right? So on the intuitive side, on the left, we've got fast, low effort, unconscious, involuntary. On the reasoning system 2 side, we have slow, effortful, deliberate, and so on. And of course, I've deliberately laid this out such that the analogy now really becomes fairly obvious, right? Because given that we now, for the first time ever on the machine learning side, have the ability to create these building blocks, to create real functional equivalents to these systems, the question is, can we extend this to a dual process theory for robots? And if so, why would we bother to do so, right? Now, you may have guessed, I certainly believe the answer is yes, we can absolutely do that. And that means we can start to examine the full gamut of cognitive science machinery related to those systems to derive real benefit for our own robots. For example, we can start by recognizing that evaluating one of our models really can be thought of as akin to a quick-fire intuitive response, allowing our robots to do things that they previously weren't able to do, or to do things that are really hard in real time, whereas previously it took forever, right? And that already is a real step forward, and we've seen this in practice already. But there's way more than that, right? Because if you're with me so far, then you might subscribe to another one of Danny Kahneman's statements, which is that intuition is recognition, which in the context of what we're talking about is starting to make real sense and have a real impact in terms of how we might architect our systems, right? But of course we could take this even further in that creativity really is association, right? And we've seen examples for that, for example, in neural network art and so on. So there's a lot of there's a lot more that we can make out of this analogy as we go forward from here. But one thing that I really want to also highlight is that much strive in robotics really comes from robots knowing when they don't know, right? So it turns out that humans are equally bad at this, which is surprising, but it is true. And yet, despite that, we can operate, we can cross roads, etc. Right? We can cross roads without getting run over. Why is that? Well, the final thing I'd really like to point out then is that if we believe that dual process theory is an analogy that we can now build in terms of the systems that we're also trying to create, then we can also seriously explore a closely related concept to dual process theory in cognitive science, which is that of metacognition, right? And metacognition is essentially a set of mechanisms that drive our own introspection. And the beauty of dual process theory is, of course, that metacognition finds a natural home here in that it regulates and mitigates the interplay between system 1 and system 2. Okay, sadly, in this really brief spotlight, this is really all we have time for, but this is such a rich vision, and I could go on for hours, but sadly I can't. I will leave you with the paper and the corresponding blog, and I really look forward to discussing this in the workshop session, and potentially over virtual beers. All right, thank you very much.